Welcome to Nitty Gritty Talks, and today we're talking about nitty-gritties of binary translation. That is going to be the number 6 in the series, where we cover the basics of different kinds of translations and specifically system-level optimizing dynamic binary translation. I'm glad to say that we will come to an intermediate pause in this series as the most basic stuff is covered, and in the outro I will mention the possible future direction that we might explore if there's going to be an interest to that. Meanwhile, I recommend to go through the other parts of the series before coming here. All the pieces come together and we can discuss different examples of what the system can and cannot do and the reasons for it. So I think it's gonna be a great learning, and let's jump into it. This example illustrates something about the good stuff which optimizing compiler can have. Of course, these examples are a little bit distilled. So we have some condition on error code, and if error happens, we just call some function which does fixing stuff and handling this specific error code. And as we can imagine, this if is not very optimal because it introduces conditional jump, which is expensive, and you have to synchronize your CPU pipeline for this. And yeah, you want to get rid of this jump, but you still have to come back to it when it is an error. And error, we suppose, is quite rare thing. So it's almost always going to the one direction. So are there any suggestions? How do we utilize the previous stuff that I talked about to achieve better performance? What's here? We just introduce new instruction which eliminates conditional jump altogether. We say check the condition of the error code, and if it's actual error now, let's go and roll back. So we suppose that everything will be always fine. We don't need to check and doing the split of the control flow, doing the conditional jump. That's that optimization called branch to assert. So we want to eliminate as much cold branches as we can, and this like error code is only one example. So for example, we just having a loop which runs a million times, and we have if something break, which is happens 1 in a million iterations, and then we probably just will change that to this throw conditionally. We will have one rollback per million iterations, and we will be able to optimize like it's there no split at all, which makes this code sequential, which makes it possible for additional rearrangements and everything. Yeah, and different optimizations exist as well, like indirect jump prediction, and we can combine this with branch to assert. For example, we can inline the target of this indirect jump if we know it, and if it's within the reach of the system. And if it's not the target, we just fold and roll back and do. So we rely on this rollback mechanism as much as possible, because it's we spend a very lot of effort in order to do that, and yeah, we want at least some juice from it. Yeah, and there are also value-based optimizations. For example, we know that this like if condition is always true, yeah, or like the registry is almost always equals 4. Why don't we assume it's 4 and do some great stuff with it, and then have the throw conditional check in order to save us from if we were not right. Yeah, and the example of fail. What could be more beautiful than eliminating 1 million instruction loop? But unfortunately, we cannot do that, and the regular compiler can in many situations. So we breed useless stuff here. So for example, this array is not used anymore anywhere, but we cannot eliminate that. And I just suggest to pause here and have a quick check-in with you. Why do you think is that? And what difference with the regular compiler makes that one to be able to remove those unneeded loads? We cannot rearrange stuff in the second example for I and G, because here we have not sequential access to the array, which is like not at all cost effective for having accesses. We want to rearrange I and G, but we cannot change the order of memory accesses because of precise context guarantee. And why do you think here we cannot change the order of accesses? And what's so bad about those accesses in the order presented? How does the precise context chime in here? And I'm not sure if it's gonna help, but basically the reason is the same as for the previous example. And again, the regular compiler does not have that limitation, depending of course on configuration options and optimization level, but it's not inherent to the static compiler. And just to make sure that we write to the same page, basically when the static compiler wants to do some kind of optimization, it doesn't have the limitations of the dynamic translator. And the things that it cares about is that the values that are used for further side effects are the same in the optimized code and the initial code that it had as an input. The top level, those side effects are remote accesses, the control flow, the generation of output in the console, these kind of things. And hence, A is an empty array, and it reads the values, does nothing with them, doesn't send it anywhere, doesn't put it in global variables, I don't know, doesn't use it, actually. Then there are no side effects and we can remove it. But in the context of binary translation, a load always has a side effect. So what happens? The process accesses the memory which was not allocated to this process. What happens if the cache does not have the contents of the page, which has the data in memory, and we have to go to the memory and fetch that page? So that affects the contents of the cache, which affects the precise context. The cache is also the state of the architecture that we have to preserve. And the last example is auto inline. Partially, I have said something about it before. So, for example, we know that the function is being called with some value, and this value is usually the same, or having two different values. For example, like in this example, it's either like 5 or 10. Just for reference, inlining basically means putting the body of the function in the place of the function call. That is done in order to remove the function call operation, which can be quite expensive. It requires moving the arguments of a function on the call stack. It requires moving them back from the stack when the function returns. When we remove the function call, we can clear up all that bookkeeping as if the code was just written in that function altogether without referring to any other place in the code. The translation happens not in a way how the code was written, rather in a way how it is executed. And I refer to auto-inline, meaning that the body is basically there already. In each function call, it's going to be part of a neighboring checkpoint, which translator is optimizing. When you think of possible optimizations that can be applied here, what comes to your mind? What would be the difference if one of the paths is taken much more often than the other, if they are taken equally? And think about how can we blend here different kinds of the optimizations that we mentioned before, like value-based optimizations, like branch to assert. So those are all the things that are applicable here, and how can they blend together in order to make the result. If both paths are frequent, we just can have two variants of function foo and optimize 4, 5, 4, 10, and then inline. Or if we have, for example, one value here, and a multiplied by 2 is not 10, and sometimes 20 or 30, but the first one is quarter, the first pass is executed much more frequently, we just go inside foo and optimize it once, and for the second one, we just don't care because it's called. So the flexibility is enormous, but also it's difficult to decide between options which ones will be actually beneficial. All in all, we discussed 3 different examples of the things that can and cannot be done. Basically, the good things that can be done in the dynamic optimizing binary translator, they're coming from the point that we can observe the dynamic behavior and we have great mechanism of rollback so that our optimistic assumptions can be validated. And if they're not right, we can go back in time and go forward again and fix where we messed up. The negative parts usually come to the fact that we have to provide precise context, which means that at any point of the program execution, we should be able to restore how this exact code would behave in the absence of the binary translator system. It cannot be any different in memory, in state of registries, or state of external devices. So I think we are in a solid place to temporarily conclude this series, and I have one possibility of an extension, which is going to be covering the historical developments of this field. So far the discussion has been fairly theoretical, and I could just make up all of that. It didn't have to be implemented by anybody or used anywhere in practice. As it appears, it's not the case at all. The developments have started in the 70s. They are still being done at the moment by different companies. They're used for different purposes. So all of that we can cover separately in the extension to this series when such information is going to be of interest to you. Overall, I'm pretty grateful to you for sticking with me. The statistics is usually so that every next video in the series gets half of the views of the people who survived through all of that. So if you've watched the whole series and you are here, let me know of any feedback that you want to give, any things that remained unclear, or any mistakes that you have found, and I would be happy to reply to any questions and maybe clarify some bits. Maybe I would see interest in some other topics that I didn't have time to cover, but just use them as if they were known at the moment of viewing. That's quite interesting actually, as a reflection back at when I was just starting the series. This journey became quite a bit longer than I would expect. The series changed 3 different places, as you can see in the background. It changed me in my state of life and like appearance and everything. So I think it's around 9 months since the series has started. So it's been actually quite a ride, and I'm glad to be here and conclude it, at least for some time. Thank you very much again, and I will see you in other series, either professional or maybe we'll just talk about something else that may be thought-provoking and worth digging. So leave any of your suggestions in the comments, and see you next time.